To record, and then we'll get started. Hey, the first question I got over the weekend a couple times was, hey, what if I'm running a little late, got some technical problems? Let me know. And the answer is get the work in as soon as you can. You know, if your internet's down, if you're out of town. I was out of town. My grading's behind, so I've given myself an extension on grading your work. And remember, on the first day, I did say you know if it's the due date is class time, right? 8:30 this morning, but I'm not going to have it graded. You know, best case early afternoon here today. But once I've got it all graded, if you now then are turning something in, well, then I've got to kind of pull out the old answer key with the rubric and make some decisions. Then I'm looking at maybe taking off points. But if it's in fairly quickly after the due date, I'm probably not even going to notice it. Okay, there may be some color coding in Canvas on stuff like that. But if your worksheets are uploaded in a reasonable amount of time, we're good to go. Now the homework though, okay, homework is due and it has a due date and it's all automated. The computer says you didn't get it in by whatever time is 23:59, 5 o'clock in the afternoon, whatever the time that the homework is assigned to be due. The computer will start taking off points if you don't make that, because that's how mastering physics rolls. And I don't really have I don't have much control over it. You know, you have to put in some kind of setting, and I said, hey, 20% a day, because I think that's reasonable. And if once I've done grading a homework set and you turn something in, that's kind of my policy. So any questions on that? I actually had two questions over the weekend on, hey, what if I got to get this thing in late? What do I do? And my answer is get it in, because it's still good for you. You know, you're going to get some points for it. And of course, the work you do here is like training for a sports event or practicing for a musical competition or a dance event. I mean, to do well in computational science, that same principle applies. I do want to again thank everybody for pointing out that you weren't seeing assignments, the pre-video that I was spending so much time recording, because now I know what I have to do. And I'm going to share, if I could, my Canvas screen real quick. And I'm under assignments. I know some people like to see what their workload is under assignments. Other people like modules. I personally like modules, but I'll just show you to be clear what happened this week. And I have no idea why, but I know what I'll do to make sure it never happens again, I guess. If you look at last Monday's reading quiz, okay, are you seeing that? I don't see a green border, so I'm going to stop share and try to do it again. That's desktop. Let's go here. Maybe you were seeing it because I was sharing the desktop. There it is. Clearly has a green border around it. So you should be seeing my Canvas screen. And this is under assignments up at the top there, which I think is how you have a screen very similar to this. And if you look at Monday's reading quiz, you'll see first, once it loads up here, that's the video I made about, remember Monday we were learning how to add vectors, which we're going to do more of today, by the way. So if adding vectors is still a mathematical weak point for you, you can go back and view this video because it's still there. Okay, and then of course you had to take the reading quiz, which caused you to look at another video, much shorter, but still a video on about vectors, and then answer a couple questions. Okay, and so that's what happened with Monday's reading assignment. Wednesday and Friday, whole nother issue. I set it up exactly the same way. And you can see up at the top there where my video was, it's not there. The two videos you had to view in mastering are still there, but my video got deleted somehow. And so what I did is I just put missing video from lesson 3.2 right there. And of course, the same thing happened on Friday, and that's what you all pointed out to me. And there's the missing video from lesson 3.3, and it's going to have a separate assignment. Any videos that I make, in addition to anything you're doing in mastering, will be so two separate assignments is what you saw for today. The first one is my video about forces, and then the second one is anything that's on mastering. Apparently I have to keep them separate, because if I try to merge them into one for one assignment, sometimes it deletes parts of it, and it being either Canvas or mastering. And it's probably when the two systems are talking to each other and linking to each other, it probably kicks something out if it doesn't like it. So that's how you'll see assignments from now on. And of course, if you know, you're not good with projectiles, for example, you still are having trouble with it, this is a video where I talk about projectile motion problems, do an example problem, and you can go review it. Just one other thing in modules, though, that I do want to show you, because a couple people asked for this. So if you go to modules, and you can I probably have a whole bunch more. I guess you don't have studio, which I didn't realize, to see videos. I have to actually put them in a module. And so if you look under projectiles right here, okay, there's my PowerPoint. So you always have my notes to look at. There's the reading quiz, which of course dropped my video. There's the worksheet itself. And then people asked for the example problem I did in class last Wednesday. And, I didn't have the video because I didn't hit the button like I did this morning, but there is my solution for that particular problem. And it's a pretty good template. Okay. And I think some of you did find it because it looked like you were either working together or using it as I was grading. I'm about, I guess, 2/3 graded on the worksheet that went along with this. Of course, I did the harder problem. I had the 57-degree angle, and you had the one that was just 0-degree angle, so it didn't have a Y component. And so those are the resources available to you. My apologies for my lack of understanding of how Canvas and mastering work together. It seemed to me to be efficient to put one pre-assignment in one system, and hopefully it would stay there. And it didn't work that way. So you'll see 2 assignments for prior to every class. And remember, this is that flipped classroom modality that a lot of people are adopting right now, because in class we're going to be working problems, which is what I'm going to be doing today, doing student polling sorts of activities. So reading and viewing these videos before class is important because it'll make everything easier on the back end, and that's the hope. All right, questions on any of that? 7 minutes spent on resources. I'm going to stop sharing that then. And I'm going to go over to my PowerPoint, and we'll do a little bit of, I got a couple polls, just 4 this time for you. And just a couple words I'm going to say. So let me share this. Screen share. PowerPoint, yes. Green border. Oh, come on, show me that green border. Makes me feel good that I know you're seeing it. Yep, okay, I got the green border. I just have to move this. Windows in Macs are not always the best thing. All right, so what we're going to be talking about are forces. And in the pre-class video, we had what we call a catalog of forces. And we're shifting gears here as we move into the 4th week and the fourth chapter in our textbook. We're done specifically talking about motion without ascribing to that motion a cause. And the bottom line is, well, what causes motion? And the answer to that question is forces. We're going to talk about Newton's laws here. And Newton's laws are pretty clear, and we'll be picking these each day of the rest of the week where we'll talk about Newton's laws. But I suspect just because you're intelligent people, you've all heard of Newton's laws. Like, let's see, if there are no forces acting on something, it either is at rest or moving at a constant velocity, which means no acceleration. So the first law talks to forces and acceleration. And if there is no force, or I should be careful, there is no net force, which is what this slide right here is talking to. If there's no net force, well, there is no acceleration, and things move in what we call uniform motion. They're either at rest or they're moving with a constant velocity. Okay, and it doesn't mean there's no forces, it just means there's no net force. And so that's one of the mathematical exercises we're going to do today, figuring out what the net force is. The second of Newton's laws is that if you do have a net force, the net force is directly proportional to the acceleration. So the bigger the force, the bigger the acceleration. The bigger the net force, the bigger the acceleration. Whenever you say something's proportional, you ask, well, what's the constant of proportionality? And the answer in Newton's laws is mass. So the bigger the force, the bigger the acceleration. However, if mass is real big, that's also in there, and that might make the acceleration less for a given force than an object that has a lesser mass, which will have a greater acceleration. And we'll talk more about that on Monday, but I just wanted to get, that's the bottom line up front. And if you've heard of those 2 Newton's laws, you're ready to solve problems. We'll talk about the 3rd law on Friday. Not very useful for solving problems, numerical problems, calculational problems. It's more a conceptual problem sort of idea. But hopefully everybody's ready to add vectors, just like we added velocity vectors or acceleration vectors earlier, or just arbitrary vectors. Forces, that will always be, those will always be quantities that we add, and forces are absolutely vectors. Okay, if an acceleration vector exists, then a force vector has to exist. All right, and our technique though in order to add these vectors and make sure we do it correctly is to draw a physical picture. Like this is a bungee jumper, I guess, and there's that bungee cord pulling upward, and the force in the catalog that we talked about was tension on a cable or a cord. And of course, the reason you fall is the force of gravity, which we call weight. And you can see the symbols that we use for tension and weight. And just real quick, the rest of the forces we'll talk about, I guess. I kind of see 7, I think. Let's see, we got tension and weight here. We've got a normal force. We've got a friction force. We've got a spring force, and springs can either push or pull depending on which way you displace them. Like the one in your ballpoint pen pushes, but if you hang something from a spring, it pulls, right? Let's see, we got thrust like from a rocket or a jet engine. We've got drag. Hopefully I got 7. Yeah, it's always hard to list 7 when you're my age because you start forgetting, did I say that one or not? We'll have a full list here in a second. But the point is, if you think you have a force acting on something, okay, like this person here who's just bungee jumped off a bridge or something, you've got to be able to ascribe a cause, okay? There has to be a tension with a rope. The earth, well, that's always there. Oh, by the way, second semester, if you come back for part 2 of this course, we'll be talking about electromagnetic forces, forces between magnets, forces between charged particles, not going to be considering in this class, okay? And once you got a physical picture like we have on the left here, you want to kind of isolate it and just draw the tension and the weight on a dot. And it may seem simple in this case, but the thing that this diagram is supposed to remind you is that all vectors that are in the same direction, when you add them up, must have the same sign. So if I'm to add up the tension and the weight, generally people think about up as positive. And so I would go, the net force vector acting on this bungee jumper would be a positive tension plus a negative weight. Everybody hear what I said there? A positive tension plus a negative weight. You could flip that around if you're inclined in a particular problem, but that's a general convention. That is the net force. So I'll always say we add these vectors, right? The net force vector is the addition of all the vectors that are acting on an object, with the caveat that vectors that are in the opposite direction must have opposite signs. So you're really subtracting tension and weight, right? You're adding a negative vector. You're adding that negative weight. We'll be okay with that idea. Great. Here's one more, I guess. And I got a skier being pulled up. I don't know if anybody's ever skied with a rope tow to get up to the top. We had a mountain like that near my hometown of Buffalo, New York, that actually had a rope tow that got you up to the top. Pretty archaic. Most people are doing chairlifts and all that now, and even gondolas. Any event, if you went to look at all the forces acting on this skier, well, that rope tow is giving you a tension, okay? The weight is force of gravity pulling always towards the center of the earth, vertically downward. You don't get to distort gravity in this world, okay? There's a normal force because the skier is on a surface. The word normal should evoke that mathematical idea of perpendicularity, okay? The normal force is perpendicular to whatever the contact surface is. And of course, friction, and we will be talking more about that. This is emotional friction as opposed to just a static friction when something's sitting at rest. And so we subscript it with a K. And if this person is moving at a constant velocity up this hill, well, then the net force is equal to 0. All right. And I guess free body diagrams are key here. Back on this slide, the difference between a diagram I might draw on the skier, just to remind myself of all the forces in the catalog, I generally draw weight right there, right? The normal force you might want to think about as being right there, right? That's where the normal force is. The tension is actually happening right there where the person is talking. I don't know where to put the friction. A lot of people say it's between the ski and the ground, right? So there's the force of friction. And you can see this diagram is different from this one, where I put all those forces, I tied their tails together, and that's how we're going to do addition, okay? And so that is what the free body diagram does. Make sure you got a coordinate system on it. It makes sure that you remember up is positive, down is negative, right is positive, left is negative, etc., and we're good to go. All right, so here's our first polling question, and this is launching the poll here. And here's our catalog, by the way. on this slide. I'll launch that poll, and obviously the catalog and all 4 questions here I think will have this: gravity, normal force, spring force, friction force, drag, tension, and thrust from the aircraft. And you can pick as many as you need here, okay? Because there's more than just one force acting on this jet on the runway, right? So, and yeah, good. It's allowing you to put in multiple answers. All right, good. I got my pen. All right, 22, 28. Excellent, 28. All right, everybody's in. We'll end the poll and we'll share the results. And obviously there are multiple right answers here, so let's make sure we got them. I think everybody said gravity, and everybody is of course right. If I was to draw my picture right there, I would say the weight of the aircraft is good to go. Some people didn't see a normal force. The normal force actually exists right at the wheel sets right there. We typically just draw it at one of them, but I don't disagree. There's actually a couple normal forces. Every place a tire hits the pavement, there's a normal force right there. An object sits on a surface, it experiences a normal force. And sometimes it'll be just kind of small surfaces. Like if you picture two hooks together, I don't know if you can see me doing what I'm doing, kind of curl your index fingers and make hooks out of them. At the contact between your fingers, there's a normal force. Okay. And so any place there's an object in contact with a surface, there's a normal force. All right, let's see what else. There has to be a thrust from the engine. And I don't even, if I use tension, I don't even know what to call this. So I'm just going to call it force TH for thrust, pushing the engines forward. And the planes I was taking this past weekend when I was out of town had at least 2 and sometimes 4 engines, depending on the size. We did commuter jets into Peoria, a couple of them, right? And so there may be actually 4 force vectors. We simplify that in a physics class to just the one, okay? We kind of think of the composite force. They're all working together. Okay, so I agree with thrust. That's how the plane moves, right? A propeller generates thrust too, not just jet engines. Rocket engines generate thrust. We'll talk more about that later. Okay, absolutely. The last one are friction and drag. Okay, and I will tell you, friction actually happens right at the wheels or like at the bearings on the wheels, and drag is just in the air. I will just kind of claim right up front and warn you, we'll often just simplify and combine the drag D and the friction F. Okay. And I guess this would be the drag and the friction would be right here. We'll often combine them into one. Now, when an object is free falling through air, like parachutists, when there is no friction, then we'll mostly talk about drag by itself. But for an object in contact with the earth, like the skier in the example I did, I only talked about a friction, and some of you may have been going, well, where's the drag? There was, we just lumped it in with the friction. So hopefully everybody's okay with that. All right, we'll move on to the next one. Stop sharing. Boom. Here's my skier again, only this time the skier is not on the rope tow. The skier is just going down the hill. And again, you want to hit friction and drag twice, go ahead. I see the first couple people in did that, and that's great. If you want to lump the drag in with the friction because the skier's in contact with the ground, you're good to go, in my opinion. But the minute the skier does a little jump or something, well, then the only force on him is drag, because as soon as he's no longer in contact with that snow, no longer any friction. So it is sometimes, it's probably more correct to include both. But absolutely, the drag is necessary when the skier goes airborne, which he's not in this particular picture. All right, 26 people in, last 27, and I'm about to end it and share it with you because I think most people are starting to get it here. And we're good. Share the results. And absolutely gravity in that normal force, right? Gravity, bloop, right there, okay? Normal force, a lot of people like it like right where the surface is. So there's the weight, the force of gravity. There's the normal force. Okay. Let's see. Friction and drag. I guess the drag would be up there. The friction is really sitting down there where the skis hit, right? It's a contact force at that instant where the skis are in contact with the with the snow. All right, now I haven't drawn the free body diagram. There's my picture to make sure I haven't missed any. And there's no springs here, so I'm not sure what people were thinking there. There would be thrust, I guess, if he had a jetpack on or something. Did y'all hear about that guy who was flying around in a jetpack by LA airport about a week and a half ago? They're like, okay, well, that's thrust. So he doesn't have a jetpack, so there's no thrust. There's no tension in this case. He's not attached to any rope, just coming down the hill. The free body diagram would look like this, right? There's the normal force. There's the weight, gravity, the force of gravity. And we'll talk about how to calculate those things later. There's my coordinate system, just a rough sketch, right? A Y and an X. Okay, and let's see, the friction force, oddly enough, would be right there. Okay, and the drag force would be in exactly the same direction. And by the way, this is a kinetic friction because he's moving. Now, if you look at these, aren't the normal force and the friction force, that's supposed to be a right angle right there, perpendicular to each other? And so it may be sensible to shift that coordinate system so that it lines up with the normal and the friction and the drag. Just kind of rotate this guy around right to here. Okay, and you'll see why here in a second. When vectors don't line up with your coordinate system, the first mathematical step you got to do is get the components of those vectors along your coordinate system. And if you rotate the coordinate system as I'm suggesting, so that it's along the lines of the normal and the friction and the drag force, well, then the only thing you have to get the components of are the weight. And so there's a practical thing that some of you will see to do right there. You don't have to, but it sometimes makes the problem solvable by making that initial step. I'll stop sharing here. We'll go on to the next slide. This is now my mountain climber. Launch the pull, forces on the mountain climber. He's rappelling down, not a real steep cliff, but certainly the side of a cliff. What force is acting on him? From our catalog there, gravity, normal, spring, friction, drag, tension, thrust. Oh yeah, he at rest right now. Isn't hopping to the next spot. He is certainly at rest. That's an odd way to put that rope. Most people use carabiners and things like that, but it'll work. $25, $20. Not moving. So that's my kind of hint here. Not moving. 27, last person, maybe not. There we go, we're in. All right, so I'm going to end the poll, share the results, and gravity again. Got to have it. Weight. There it is. Okay. Absolutely a normal force. Okay. It's kind of an odd thing here, but there's my surface, right? And so the normal force through both his feet, but we'll just draw it this way. The normal force is going up that way, right? Okay. There's a rope here. So there must be a tension that many of you identified. So there's the force of tension. I disagree with drag in this particular example, but I do agree with friction. If these other forces here would tend to make him slide down the hill, okay, or down the side of the cliff at both of his feet, there could be a friction. Since I said he's at rest, this would be a static friction and at both his feet. And again, even though there might be two contact points with two friction, we generally draw them together, okay? But so I don't disagree with friction, but since he's not moving through air, I would disagree with drag. Okay, and he doesn't have a jetpack on, so I think you're messing with me with the thrust. All right, so let's draw the free body diagram here. There's the tension. There's the normal force. They look sort of perpendicular, don't they? Yeah, so I'm not 100% certain of that. They don't have to necessarily be, but the way I drew them, they seem to be. There's the weight. Okay, there's the weight. And the thrust and the friction force seem to be in the same direction. So there's the static friction force, okay? And there's the dot representing the person. And I guess the only thing else I need to put on here is a coordinate system. And again, this might not be the best coordinate system. X and Y here might not be the best, but it does remind me that things that are going in one direction should be positive, things that are going the other direction should be negative. And that's key to these problems. Throughout the rest here, rest of the week, and as we continue on next week and the week after doing Newton's Law problems, don't forget that vectors in the same direction must have the same sign. Vectors in the opposite direction must have the opposite sign. Stop sharing. And we'll move on to my last one right here. 4, one more of these, and we'll do some math because we love math. Launch the poll. All right, so we got this mass here, and so we're looking at the forces acting on that mass. And key word here you'll see in a lot of physics problems, rough surface. So think about this as being a rough surface. It's not an icy, smooth surface. And that evokes, those are terms of art that are meant to evoke a response from you, okay? It's part of the given information in a problem statement. All right, 25, 27, one more, and everybody's in. We'll end it and share the results. Has there been a problem that didn't have gravity? And you almost got to expect it. So there's the weight force, gravity. Okay, the normal force, absolutely, it's sitting on a surface. Got to have a normal force if there's a surface involved. And okay, is there a spring force? Yes, I saw this spring as being stretched a little bit, and so I had the spring force pulling that way. So I absolutely agree with the spring force that just about everybody picked. Okay, the word rough, okay, tells you that there is a friction force, and I can't tell you which direction it is unless I know which direction it's moving. And so let's say the spring is pulling it to the left, that would put a friction force right there going to the right. Assuming it's moving, it's kinetic, okay? Drag force, possibly, there is wind right here, so I can't say no to that one, okay? But often when things are in contact, we'll lump those two together and just think about the drag being included in the friction. And in terms of tension, about 11 people went with it, okay? The spring force is absolutely a tension force as opposed to a compressive spring force, but tensions, when we talk about T, we mean some kind of rope or string, okay? And so in this case, it's a spring. It's doing the same thing, but there is a difference. A spring will apply a greater force the longer you stretch it. A rope, just whatever force you pull on it with, it is exactly what is transmitted to the object. So the reason I think if you're worried about this, the difference between spring forces and tension, spring could be variable, whereas tension is a constant force, okay? And that's just something to think about, and that'll be more clear hopefully as we move forward. Any questions on any of these? I see nothing in chat so far, and so I'm hoping everybody's happy. This is the first day of forces, but this math here, some of you probably aren't going to like that. So I'm going to put the polls away. I'm going to put PowerPoint away, and with any luck, I'll be able to start sharing my iPad with you where I'm going to work a problem here, and it's the first worksheet problem. So let's do iPhone via AirPlay. Come on, AirPlay, work for me. Screen mirroring. Looks like it's working this Monday morning. All right. And I can put that away. And so I think you should be seeing the worksheet for today. And I'm going to do the first problem right here. And the second problem, and I got a complaint from one of my modern physics students. I'm not giving you enough room to work the problems here. So I'm just spreading it out, okay? It may waste a little paper. Problem 2 is the problem you're gonna have to work, and there should be a few minutes at the end. We'll break up into groups, let you work in groups. And then there's the, well, that's supposed to say 3, because that's what comes after 2. I love the way Word renumbers things for me, okay? There's some editorial words that are meant to help you here, and same before the problem I'm going to do, okay? So one thing you'll notice, I said in today's worksheet right here, allowable forces are today weight, gravity, friction, spring or spring tensions, and normal contact forces. So I've thrown out drag and thrust. So absolutely, if you think there's a friction force and a drag force together, just consider them one. And we're not going to have any jetpacks or airplane engines or anything like that. So that's coming later. So those are your forces to play with today. But in the first, and that's for the third problem, which I see now is a typographical error for 4. And so here's my first problem. All the things I said should be the other notes, okay? Free body diagram separate from any system sketch you might draw. Remember, a free body diagram ties all the forces together to a dot and has a coordinate system, okay? Make sure you got that coordinate system. Make sure you're paying attention to directions of vectors. All right, so here's the first problem though. And I got to calculate the net force for an object which is experiencing 3 forces. Go away. I hate the iPads do things. They put notes right over my toolbars. It's telling me I have class today. Thank you, calendar. Can you go away? Yeah, there it is. And so now I can get to my tool. Oh, now it's telling me that Zoom is having a meeting and somebody turned in a late assignments. You love Apple. Thanks for letting me know. All right. So what's the first thing we should be thinking about when we see a problem like this? 30 Newton force directed along the plus x-axis, okay? 40 Newtons directed 27 degrees off the y-axis, 50 degrees directed along the minus y direction. Can anybody picture that in their heads? I got to be honest with you, I've been doing this for over 40 years. I can't. But I remember I tried to draw this when I was practicing, and then I went, oh, wait, I'm drawing that wrong. So let's get it right. And they're labeled A, B, and C, so I'm going to call them A, B, and C. And so the first thing I guess I should do is draw a coordinate system. Okay, and there's X, and there's Y, and I make it dashed. If you look in my notes, I said, make your forces darker. And if you can't do that, just make your coordinate system dashed and make your forces solid. And try to draw the arrows that represent the forces roughly the correct length. And so if you look, the first one's 30 along the X, so it is actually the shortest of the 3. And so there is vector A, right? And I should put a little vector hat on, which you can barely see, okay? Let's see, what else do I have? I'm going to jump right to the C because it's the next easiest one to draw. It's longer than vector A, probably not quite as long as I've drawn it, but there's vector C, right? And then the last one, the one in the middle, 40 Newtons, so it's in between the length of A and C, okay? And these don't have to be measured with a ruler or angles with a protractor, but let's see, it says 27 degrees off the plus y-axis into the second quadrant. And so I don't know, maybe right about there is the vector, that's supposed to be a straight line, is the vector B. Everybody okay with that picture? Good, we're good to go here then. That's the picture. I'm gonna try to make it a little smaller. So the smaller tool here is that, and then I can resize it a little bit. And so it's still there even though not, and I can put it off to the side so I got some room to work. Got to be able to draw that. And oh yeah, I didn't label, but maybe I should. Where's the angle? The 27 degrees is right there, right? That's where the 27 degrees is. All right, so one of the things we said about horizontal and vertical vectors, ones that are along our X or Y axis, pretty easy to get their components, right? And so what's A sub X, the X component, and what's A sub Y? And I recommend you write this out, not try to do it in your head. You'll make mistakes if you try to do it in your head. A sub X, 30 Newtons, okay? And by the way, a Newton is the unit of force that we're going to be using throughout the rest of the course. Sometimes in chemistry and some other courses that deal with smaller things, dyne is also a unit of force, but Newton is the answer. And we'll give you exactly what a Newton breaks down to later in the week. What's the Y component for vector A? Well, just look at it, hopefully. That's the value of that diagram. It doesn't have a Y component. Its Y component is 0. All right, B is going to be the hard one, right? B is where we're actually going to have to do some math. So B X component and B Y component, they're going to be difficult. I'm going to hold on them for just a second, and I'm going to do C, okay? C is 50 newtons directed along the minus Y. All right, so let's write, I got to change my toolbar. Let's write CX and CY. And sometimes the strategy is take care of the low-hanging fruit, right? All right, well, first question, I guess, is does the vector C have a component along the X direction? And the answer is no, it doesn't. 0 newtons, right? It doesn't. What's its Y component? Okay, well, it's 50 newtons, but it's downward, and I've made the y-axis, I made positive upward, and on the x-axis, I made to the right positive. And so since CY is downward, it would be minus 50 newtons. Everybody okay with that? We had a similar issue with the projectile motion problem. Remember, as the ball or whatever the object was came off the cliff, for both your worksheet problems last week, there was only an X component to velocity. So the Y component of velocity was 0. It was horizontal, just like vector A is horizontal. Some people didn't quite like that idea. You got to realize I'm trying to make it easy for you, because let's look at vector B here. Okay, vector B is the hard problem, right? Let's see, and it's 40 newtons. Okay, so it's going to be the magnitude of the vector, and it's either going to be a sine or a cosine. So there's going to be an angle, and then it's going to be 27 degrees, right? And so which trig function am I going to do in order to get the X component? And you look and you go, well, the X component is, maybe I should go with a different color here because I can do that to help you out. The X component is right there, right? And if I made a triangle right here, okay, I'll draw it off to the side. There's the vector B. There's the X component, that's B. And of course, there's the Y component. And there's the 27-degree angle. You can see that the X component is the opposite side. And hopefully you realize the opposite side means the sine is the appropriate trig function. Now there's one other issue here before we're done, okay? The X component is pointing to the left. As I went through, I said we're going to make positive X to the right, and so that has to be negative. And in order to get this problem right, you got to remember that. By the way, for those of you that are mathematical purists, you may say, well, that angle actually is 90 plus 27. It's 117 degrees. And if I put 117 degrees into my calculator, that negative sign will pop up automatically for you. You're absolutely right. It will. Okay. So if you want to take that extra step, either you have to remember to add 90 because you're in the second quadrant to the 27. Okay. Or you got to remember to put a negative sign on yourself, whatever you want to do to make sure you remember that. But whatever you put into your calculator, make sure at the end that it makes sense. You're in the second quadrant, the X component has to be negative. All right, so then if I've already used the sign now, and these are newtons, right? And by the way, I did this in my calculator and I got minus 18.1 newtons right there. Let's shift back to a more pleasant blue here. Let's go to blue. And so now for the Y component, it's 40 times, it must be the cosine of 27 degrees, and that's in newtons. And when I put that in my calculator, I got 35.6 newtons. Okay, and it's upward, right? It's upward, so it stays positive. And so armed with all this now, we can finish up the problem. We can get the answer, right? And I got to go to that button. I'm figuring out this notability thing. I really like it. Okay, so how do I get the resultant X component? Okay, so I don't know, what do you want to call the resultant? It's a force. Let's call it the net force. How's that? So the net force, and how do I get the X component? Well, I take A sub X plus B sub X plus C sub X, and I add them all together. All right, and so let's see. I've forgotten already, so I got to scroll up. A sub x is 30 newtons. B sub x minus 18.1 newtons. And C sub x, that's the easy one, 0. And so when I added those two together, hopefully what I got, 30 minus 18 will be 12. It's 11.9, I guess. 11.9 newtons. Okay. And then the force net in the y direction is equal to, well, the y component of A plus the y component of B plus the y component, plus the y component of C. All right. And so let's see, that's going to be, I've forgotten already again. I better scroll back up a little bit. Y component of A, that was just 0. Okay. Y component of B, 35.6 newtons. Okay. And then the y component of C, I'm going to just subtract it. It's plus or minus 50 newtons. Okay. And when I add those two up, I think what I got, it's about 15, less than 15. So it'd be minus 14.4 newtons. And let's just scroll back up to see if I answered the question. Am I done right here? Do I got to get a magnitude and direction? I don't remember what the problem asked. So let's make sure we've answered. Okay, so I'm given these three vectors, which I drew. Draw a sketch. I did. Find the force by vector addition. Oh, we don't know what the acceleration is. So let's see if the second problem says it. I can't make you do accelerations yet because we don't have Newton's second law in place. But if I'd given you the math, by the way, you would just divide through by the mass. Those of you that know Newton's second law can do that. So we'll avoid acceleration, but that's a harbinger of things to come, isn't it? Because once we've got Newton's second law, I'll give you the mass. You take the net force, you divide by the mass, the two components of the net force, you divide by the mass, and you would have the acceleration. So other than the fact that I stated the problem incorrectly, I actually wrote this on a plane. So forgive my typo here, but let's see what the one you're doing says. Yeah, yours is correct. Yours, the problem you're going to do here is exactly the same thing. You're going to calculate the net force, okay? But you don't, it doesn't say acceleration. And I guess the difference is where the forces were oriented. And I guess we went 50, 20, 100 is the three forces oriented as shown. And then the last problem you get to do is just draw a free body diagram, okay? I think that's what this says. So you got this crate here. Doesn't matter what the mass is because we don't have Newton's second law, but we got a cord that's pulling at a 29-degree angle. And you just need to label all the forces acting on the crate and draw a free body diagram, just like we did in the polling today. Nobody said a word in chat, so I'm just hoping everybody's happy. So I'm going to split you up into groups to work for we've got about 5 minutes, 6 minutes, I guess. You don't have to we're not going to present today. Just give you some time to work with people and ask questions. I will say this, when I do this in my modern physics class, I jump into one of their groups, there's a lot of conversation. Feel free to share ideas with each other, at least get the drawing right. Because if you get the drawing wrong in the next 5, 6 minutes, there's no way you're going to be able to get the problem right, okay? One other thing I do want to say, for those of you that have had a little bit of math, you may wonder, why doesn't he just decide to use these things called unit vectors? Because it does help you remember the rule, okay? Our textbook doesn't make a big deal out of them, but there is a mathematical notation set that forces you to think about this. There are things called unit vectors. The one in the x direction is I. And so when I write these components out right here, anything that has an x, a typical thing to do is say, well, it's an I. This is a J. This is an I. This is a J. Okay. And this is an I. And this is a J. And you just add all the I's and you add all the J's together. You keep the components separate. It's just a notation that helps you remind to keep the X's and the Y's together and add all the X's, add all the Y's, okay? If you've never used that notation and it's just gonna be getting in the way, don't worry about it. But if you understand vector notation and you've seen that in a math class at some point, that's why the rule is what it is. All right, I'm gonna stop talking. I'm gonna go to stop sharing here. and I'm going to go to hopefully breakout rooms. And I'm going to make, looks like 8's the right number. And you can go just draw your diagram. You got about, what, 4 minutes left. Make sure you got your diagram, and then everybody's free to go. Open all rooms.